Well, we've been looking at arc length, and it can be defined this way, where we calculate the arc length for the integral from x equals a to x equals b, and then we have this square root of 1 plus the square of the derivative of f of x, and that gives us the length of the curve from a to b. Now, today we're going to expand that to look at how this relates to the area for the surface of revolution. Now, this part right here we can essentially call ds. And I'll kind of blow this graph up a little bit and take a look at what ds represents. We're essentially looking at just a tiny little piece of this curve, and the smaller it gets, the straighter it gets. And we can kind of almost say it's going to be the hypotenuse of this right triangle. And we can say this is delta x and delta y, and then the ds, well, technically it's not ds yet until we take the limit of it, so let's make that a delta s. Delta s would be square root of delta x squared plus delta y squared. And then there's a lot of fancy algebra that we go through, and we end up with ds once we take the limit as this delta x approaches 0. That's going to equal the arc length here, adding all of the delta s's up. And this same idea is used with the area of the surface of revolution, except we'll have an area to look at rather than just the length, very short length. So let's take that next step up. We'll revolve this arc length about the x-axis, and we're not doing volume this time, but we're going to look at the surface area. So if we go ahead and revolve that curve around the x-axis, we would create a three-dimensional object. And again, it's just going to be the outside part. We're not looking at the volume. We're not revolving the area, but just that I guess you could say one-dimensional line to create this shell. Okay, and we want to find the surface area. Well, to do that, we're going to need to, again, the idea, take a local estimate, a slice, however you want to call that, and we'll take this little piece of arc length that we talked about earlier and see what that does when we revolve it around the x-axis. Well, we'll get this little kind of ring. Okay. And in thinking about that ring, kind of just pull it out here to the side. Now, to find the area of this, what we're going to think about here is, let's cut this and roll it out. So there's our cut right here. Roll it out flat. What are we looking at? Okay, it's just going to be a rectangle. Or at least very close to a rectangle. Theoretically, it would not be a perfect rectangle, but the smaller that slice is, the width of the slice, the closer it's going to be a rectangle. Now, to find the area of this slice, the area of this rectangle is simply length times width, but how does that length and width relate to where that slice came from? Well, we can think the width, we'll let that be the delta x. Okay, just the, actually, instead of letting that be delta x, it would be better to think of that as delta s. That small little arc length that we had looked at leading up to this point. So the width will be our delta s. The length of this would be what? Okay. The length of that, well, think about it in terms of that ring. We slice it and lay it out flat. The length is actually just the circumference of that circle. And the circumference we can represent as 2 pi r. Okay? And as we look at the original picture, what does r represent? Well, that's going to be, let's look at it in this case, that's going to be the y value that we're dealing with. And in this particular case, we want to turn this into terms of x. So the radius is going to be f of x. So our area of the surface of revolution here, I guess we'll say delta A, the area of just that little slice, is going to be length times width, or we'll just leave it in terms of r for now. And then as we add up all of the slices along that curve, our integral from A to B, theoretically, the summation of all these little slices, and as delta S or delta X approaches 0, we can turn it into this integral from A to B of 2 pi. Now in this case, the R is going to represent f of x, and the delta S, or ds, once we turn it into this integration, ds represents the same thing we did with the arc length. What's the formula for the arc length? So this would be the formula that you use to find the area for the surface of revolution. Now that's revolving around the x-axis. Now, if we revolved it around the y-axis, theoretically it would be the same thing, but the formula is going to look a little different. Let's see what happens on our next page when we revolve it about the y-axis this time. Again, we can use the same arc length, or the same length, but this time going this direction, we'll have a different figure to work with.
It's the same picture though, right?
Well, this direction would be this part. So it's the same arc length, but the three-dimensional object is going to be different because we're revolving it about a different line. Now the idea here, again, look at our slice. Okay. And, well, we said delta A would be equal to, I guess we don't need the approximately equal, delta A for that slice would be equal to 2 pi r times the delta S. Still the same basic formula. Length would be, well, the radius, or not the radius, the circumference of that circle. And the width, well, the width can still be represented as delta S. Now we'll be able to do this a couple different ways, but we'll keep it the easy way. We want to do things as easy as possible, right? Or maybe as less difficult as possible. Some may argue that there's nothing easy with any of this, but there are some less difficult things anyway. Now, R in this case would be what? It's going to be our x value, whatever x value we're dealing with. Now, our function is defined in terms of x. So we really don't need the f of x to represent r, we just need x. And we don't really need to change it to terms of y. We could, but the function's already in terms of x, so let's leave it in terms of x. Why can we do that? ds is that no matter where we rotate the arc length about, ds is can always be represented this way. So if we're revolving this line or this curve about the y-axis, we can still leave it in terms of x. Don't think about this thickness as dy. We need to think about it as ds, which was our arc length formula. And we only have to multiply that by 2 pi r to get our area. So in this case, the surface area, since we're still in terms of x, we can integrate from x equals a to x equals b of 2 pi times x. X again was our radius, and then times ds, which would be this. So this represents the formula for the surface area revolving an arc length around the y-axis. So notice in this case, it's not f of x, but it's just x. The radius is going to be the key part here. ds can always be represented this way, no matter where we're revolving the arc length about. But the radius is what's kind of tricky. Got to figure out, is it represented by x? Is it represented by y? If it's represented by y, because we're integrating with respect to x, we've got to substitute in the function y equals f of x. We've got to put the f of x in there. But if we're revolving about the y-axis like this one, the radius is just x. Okay? Questions?
Can you work that one? Do nothing?
The only work to do here, whatever f of x is, let's say, it kind of looks like maybe the square root curve. We'll say f of x equals square root of x. We'll take the derivative of the square root of x, plug it in here, and then from whatever a is to whatever b is, plug those numbers in, and that's your integral. Then you got to go through the integration, whatever that ends up being, but there's nothing to substitute in here. We've already got our x. And many times, because of that radius out here, outside of the square root, the integration actually is a lot easier than what you've been seeing with just the arc length. Because a lot of times, whatever we end up with under the radical, if we can let u equal that, then du, usually this gets taken care of with du. Without that x out there, or without the radius part on the outside, substitution usually doesn't work. Like I said, as you've probably seen already with arc length. Arc length is actually a harder integral to do than the surface area. So that's a little bit of help for you, but that's how we calculate the surface area when we revolve a curve around some line.